How you doing? I'm Mr. Rose, and today we're going to talk about Kepler's laws. Now, you might be thinking right away, I see a bunch of energy stuff on those boards, and that's true. Because to really understand where Kepler's laws come from, we have to step back and really understand conservation of energy and conservation of momentum. So to start, we're going to talk about some conservation of energy, and I'm going to sit here a little bit and go through nice and easy to ease us into this universe known as Kepler's laws. So, we know thus far that conservation of energy is a fundamental theorem of physics. We know that everything is kind of ruled by these conservation laws in energy and momentum. And Kepler's laws are no exception. So we know in general, conservation of energy, wrong side, conservation of energy is just my kinetic energy plus my potential energy. Well, we know kinetic energy is kinetic energy. In other words, it's always 1/2 mv squared. Kinetic energy is always moving. U, I know there's a little glare there, so I have U for my potential energy. Well, U is positional. Potential energy, there are lots of different kinds of potential energy. The two I have here as an example are just gravitational potential energy or elastic potential energy. And we'll dive deeper into gravitational potential energy in this chapter. Now, what we know is if I apply Newton's laws through just one dimension right now, just only say in a horizontal x direction, I know by definition a change in kinetic energy is F dot dx. Well, that's just my work kinetic energy theorem. So my change in kinetic energy, K2 minus K1, is equal to the integral from x2 to x1, summing up all those forces along this path. This is my work energy theorem, my work kinetic energy theorem. I also know that if I do some work, I can change an amount of potential energy. So I have my potential energy at x1 minus my potential energy of x2. Rearrange that, I get my nice conservation of energy here. I've got kinetic energy before, K1 plus U1 is equal to kinetic energy after, K2 plus U2. And as long as I have no friction in an ideal system, that holds true. Friction isn't that big of a deal for us to deal with. I know that if I add friction into this mix, I have my energy total final, K2 plus U2, minus my initial energy, K1 plus U1, is equal to, if I have some frictional force, I know F dx, I know that has to be based on position. In other words, if I know the path that I'm taking, I could figure out how much work or how much energy I lose to friction. So I have the integral of F dot dx, where that is the path that I'm taking. That would only be if friction is introduced into our system. Well, up on my left here, or your right of the screen, what if it's not in one dimension? What if I start at R1 and I make it to R2 and I go one of two different paths? Well, I know my conservation of energy, change in kinetic energy, is F dot dr. And I know that I may now have multiple components, say x components and y components, which means I have f dx, fx dx, and fy dy. So I know my work kinetic energy theorem, K2 minus K1 is the integral of f dot dr, and that's easy to show. That's easy to show true. But what about the other half of the equation? What about my potential at 1 minus my potential at 2? Well, clearly, I have two different paths. That might not work because it's easy to prove that part is true, but what about taking my path? If I go path 1 or path 2, that could be very different. So it seems like there's a problem, but I also know that I can't break physics with just some simple two-dimensional drawing. In other words, there's a new hope. It's not really a new hope. I just got a Star Wars theme going on. I know by definition that my force is some change in energy. So if I change my energy du over dx in the I hat direction, minus du over dy in the j hat direction, I know if I find those components, the components of my force, well, they all have to add up. And if they all have to add up, it's not going to matter if I take path 1 or path 2. In other words, very simple, as we may have learned years ago, it doesn't matter how I get there. If it's a conservative force, all that matters is that I get there. So if I take the left side of my equation, my f dot dr, my left side of the equation, due to the nature of a dot product, if I add up all my appropriate components, I prove that u1 minus u2 is true. A simple analogy for this we've spoken about before, it's like walking around a mountain. You can take multiple paths up a mountain. I don't need to know the path. All I need to know is that I track some different height on my mountain, which essentially means for every force who has an integral that is independent of path, there will always have an ancestor for that in potential energy. In other words, this F equals negative du over dx in the I hat direction plus negative du over dy in the j hat direction plus negative du over dz in the k hat direction will always be true in nature as long as it is a conservative force, which means friction doesn't work so well, but things like gravitation and when we get to electromagnetism, an electromagnetic force will work really well. So that gets us to the big picture of gravitation. So we're going to travel back, I'm going to get up now, a little through time back to Newton and see what Newton does with all of this information. Newton was like really smart. So here I have a wonderful picture of the sun, the moon, not the moon, the sun, Mercury, Venus, and Earth. We know that that's Earth because it's blue. We know that Earth is the third rock from the sun. And back in time, say during Copernicus's time, he was one of the first to postulate the sun was in the center of the solar system. He knew that, he believed this to be true. And if you ask me, if you ask you, all of us actually know this to be true today. How do you know this to be true? You know it, I know it because people have told it to us. It's really difficult to prove. So it was years of scientific research that proved this fact. All starting with Copernicus. Sorry for being off screen, just trying to move some stuff out of the way. All starting with Copernicus. So what Copernicus did was take years of data and revolutionized what we had. He really just took stuff that we knew about the Earth being the center and switched it. Transcribed it and to the sun being the center, made some data calculations or some approximations, I suppose I should say, to postulate that it's not the Earth but the sun in the center and everything is rotating around that. What do we do with that? He made some jumps, it was very unpopular. Well, what we do with that is we add a rich guy, not so good at math, but has a lot of time on his hands and loves astronomy, in Tycho Brahe. Some cool things about Tycho Brahe. Number one, he had an iron nose. In other words, and the reason why he had an iron nose is he lost his nose in a sword fight. Someone cut it off, and he had a strap-on iron nose. Second thing about Tycho Brahe, again, he was a spoiled rich kid. Lots of money, his own lab, really bad at math. He died of a bladder infection or a burst bladder because he was sitting next to the king, and I don't know how this is possible, but it was not a good thing. It was insubordinate to get up before the king, so he apparently needed to use the restroom very badly, didn't get up, his bladder burst, he died of a bladder infection or urinary infection, something like that. Look it up, it is actually true. So, what Tycho Brahe did is he took tons of data, about 40 years of data. He had an assistant. That assistant was Johannes Kepler. And what Kepler did, very good at math, but just poor as opposed to Brahe, he took all of this data and went from Copernicus, sun in the center, Earth moving around, taking all this observational data to come up with three laws. His three laws are written on the board here. His first law is the law of elliptical orbits. We know today that the Earth, as well as all the other planets, go around the sun in some kind of elliptical orbit. Well, this is a picture of my elliptical orbit, and this is what Kepler was able to come up with. We have two focal points, F1 and F2. The sun is at one of these focal points. And at one of the, from the side to the center, I have labeled A. That is called the semi-major axis. The length, or the total size of my elliptical orbit, the long way, is 2A, or twice the semi-major axis. From a hemisphere, the center to the top, the center to the bottom, a hemisphere up or down, that'd be labeled as B, or the minor or semi-minor axis. The total height, I suppose, of my orbit would be labeled as 2B. So, law number 1 is that planets traveled in an elliptical orbit. Law number 2 is that planets didn't go the same speed. Planets actually sped up and slowed down. So if you look at this picture here, I have a planet that goes from 1 to 2, and some later on I have a planet that goes 3 to 4, with the sun being at that focal point. Well, what I tried to show you here is that the red area here would be the same as the blue area there. In other words, the area swept out by the planet per unit time is constant. If this happened in 1 week, that also happened in 1 week. Meaning, again, my planets speed up and slow down as they go around their star. Law number 3 is called the law of harmonies. Law number 3 is I take the period of rotation or revolution all the way around my sun from point 3 all the way back to point 3. I square that, divide it by the cube of my diameter, or the semi-major axis. That cube is the same for all planets. You can look up all the data for our solar system. You can test it yourself. It all comes out to be relatively the same. So those are Kepler's 3 laws that I offer to you now as just fact. We will get into them a little bit more in the future. What we want to know is what these 3 laws had to do with our buddy Isaac Newton. You may have seen this formula before. F equals gm1m2 over r squared. Now there's a lot of stuff going on here, and I may abbreviate some. So this is usually presented to students as just fact. This is what we know. It's not really the best formula. So let's go back and start talking about it. What did Isaac Newton know? Isaac Newton knew that here's the sun, and he knew that our planet went around the sun lots of times in some elliptical orbit. He simplified things. Elliptical orbits are hard. Circular orbits are easy. So what Isaac Newton did, I'm just keeping track of my notes here. Sorry about that. What Isaac Newton did is he postulated, he said, the Earth moving around the sun is very similar to the moon moving around the Earth. And what you may remember from a lower level physics class, that whole apple falling on Newton's head. Not true. But he also postulated that the apple falling to the Earth was similar to the moon orbiting around the sun, or the moon not the moon around the sun, I'm sorry, the moon around the Earth. And the moon continually falling towards the Earth. So we have layers of comparisons for our buddy Isaac Newton. Now, we knew about centripetal force, just classical mechanics. It's also want to point out that classical mechanics goes from boxes on inclined planes to celestial mechanics and planets orbiting around the stars. That's a pretty big jump and a wide range on how powerful classical mechanics can be. So we have our moon orbiting around the Earth, and we're going to compare it to the apple falling from the tree. We know about centripetal force. We know that the Earth is moving around. We don't know why. So Newton postulated that it is the sun that is forcing the Earth to move around in that bended circular path. It is the Earth that is forcing the moon to rotate around in that circular path. That's what we're going to work with. And we're going to work with stuff that we knew. So what exactly do we know? We know, and Isaac Newton knew, that for our apple and our Earth, there are 2 things acting on each other. We have a mass of the apple, we have a mass of the Earth. And we know, just like I tried to postulate earlier, we know that there is some dependent force. The force that the apple falls down is path independent. So if I know the force and the path, this is a function of force versus distance. So I know I have a net force, F equals the mass of the apple, the mass of the Earth, and the distance from the apple to the center of the Earth. Things that we know. We knew the acceleration would be 9.8 meters per second squared. We knew F net equals ma. After all, that was just an application of momentum, so Newton knew that. And we knew Newton's 3rd law as well, that forces act on each other. So whatever force the apple is pulling on the earth is pulling on the apple. So with these things, it's easy to say, well, F equals ma, the mass of the apple, times the acceleration of gravity on Earth is equal to the mass of the apple, the mass of the Earth, times the path that the apple is going to take on Earth. We can make an acceleration equation for that apple to be mass of the Earth times, again, a function of the distance the apple is going to travel towards Earth. Since we're making a comparison of the apple to the Earth and the moon to the Earth, we can make the same comparison to find the acceleration of the moon around the Earth, or the sun around the moon. So we have a very similar formula. The acceleration of the moon, mass of the Earth, times a function of the moon's rotation around the Earth. And again, we can figure out what that path is. So to compare these two things, we're making a simple ratio. He took the acceleration of the apple that we know here on Earth, the acceleration of the moon, no idea what that is, and we are just making a ratio, one to the other. I lose the mass of the Earth, that's unimportant, which is good because I didn't know what it was, and now I have a function of how far away the apple is from the Earth, and how far away the moon is from the Earth. I know the acceleration of gravity here on Earth. We could have tested that to be 9.8 meters per second squared, and things that we also knew. We knew that the radius of the Earth was about 4,000 miles. We postulated or figured out that the moon was about 238,000 miles away. So I can set up this nice comparison to figure out what the acceleration of gravity on the moon is. To do that, I have no idea what the velocity of the moon is going around the Earth, but I do know that it's simplified into some circular orbit. So I know its distance over time, 2 pi r divided by t. I divide that by how far away it is. I get a velocity of the moon around the Earth to be about 1,000 meters per second. I plug that into my centripetal acceleration, v squared over r, and I know I get an acceleration of about, I'm off the screen, an acceleration of about 0.0026 meters per second squared. About 3,600 times less, or the acceleration of the apple is 3,600 times greater than that of the acceleration of the moon. Well, one, that number is way off. Why is that number way off? Well, we know that we have some rotational motion and a translational motion. We didn't account for that. But what we also can figure out is the moon is about 60 times further away than the Earth is from the apple from the center of the Earth. So if I take this number and I multiply it by, I take that number and multiply it by 3,600, I get about the acceleration of gravity. If I know how big my distance is, my path-dependent distance is, Newton came up with his simple comparison. I know that was kind of poor, but Newton came up with a simple comparison, knowing that the masses are related to each other. The force that each mass has to feel is the same. This equation is missing something. It's obviously missing that g. Newton didn't know this g. G is negative 6.67 times 10 to the negative 11th. Yeah, I think that's right. 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. It's a really small number. We had no way to measure that. But what Newton was able to accomplish was a really nice comparison about how big things are relationship-wise to other things. This G didn't come about until Henry Cavendish, way after that. And Cavendish figured that out by using two masses and a vat of mercury, actually. So Newton came up with this in his time. Easy comparisons. And being able to figure out that there is some ratio that exists and those forces exist. And those forces always have to be the same on each. A couple of things we need to figure out in our next lectures. Where did that negative come from? I just snuck that little negative guy right in there. And how does this negative, how does this apply into Kepler's laws? That's all I have for you today. It was a very broad introduction. By all means, please feel free to like, comment, or subscribe, and keep your questions coming. You'll see me next time.